This is your presenter Asloob Mudassar, and I am presenting slide number 18 of the course on laser physics. Question: what properties of laser beams make them distinct sources of light? Describe them briefly. Answer: there are four fundamental properties that make laser beam a distinct source of light, and these are monochromaticity, coherence, directionality, and brightness. Monochromaticity means single color, which actually means a single frequency. If lasing action occurs between two levels with energies E1 and E2, such that E2 is greater than E1, then the single frequency of the laser beam is defined as nu is equal to E2 minus E1 divided by h, where h is Planck's constant. Active medium in a laser source is placed between the two mirrors and form a resonant cavity. Laser oscillations occur at the resonant frequencies and satisfy the condition capital L is equal to capital N times lambda by 2 is equal to capital N times C over 2 nu, where capital L is the length of the laser resonant cavity, capital N is an integer, and lambda is the resonant wavelength. A large number of resonant wavelengths with different values of n can satisfy the resonant condition given by equation number 18.2. The lasing frequency given by 18.1 is the dominant frequency in a laser beam, and in addition some neighboring frequencies satisfying equation 18.2 can also be present in a laser beam. A laser beam with a few resonant frequencies present in it is still regarded as monochromatic. Coherence. The concept of coherence may be viewed as spatial coherence and temporal coherence. We first describe spatial coherence. Consider 2 points P1 and P2 on a single wavefront. You know that wavefront are the surfaces with constant phase of a laser beam. So P1 and P2 are located on a single wavefront. By definition, the values of the phases at the points P1 and 2 must be the same, and the phase difference, which is delta phi is equal to phi 2 minus phi 1 is equal to phi minus phi is equal to 0. If delta phi is equal to 0 for all time t greater than 0, then the points P1 and P2 are regarded as in perfect spatial coherence. So you see that this is the case when the 2 points P1 and P2 are located on the same wavefront. The definition of spatial coherence is valid when there is only a single value of a phase over the single wavefront. When a laser beam propagates, then on its way the propagating wavefronts may be distorted, and the distorted wavefronts may have varying values of phases with time at different positions in space. For such a condition, the spatial coherence is defined as: consider a point P on the wavefront and consider an area segment centered at point P such that all the points within that area bear a constant phase relationship with the phase value at point P, and that the phase relationship does not change with time. Then the area around such a point P on the wavefront is known as the coherence area, or more accurately as the spatial coherence area. The wave is said to possess partial spatial coherence. Next we describe the temporal coherence. During the stimulated emission within a laser cavity, the emitted waves oscillating within the resonator are amplified and emitted through the output coupler in the form of wave trains of finite length. 3 consecutive wave trains from a typical laser source are shown, each of temporal coherence equal to tau naught. So you can see that these are the 3 wavefronts, these are the 3 wave trains emitting from the laser, and these are consecutive wave trains which we have shown. each of extent equal to each of time extent is equal to tau naught. And you know that we have shown P1 and P2 any 2 points on the same wave train. At point A, at point B, at point C and point D, there is a discontinuity between the wave trains. So a mismatching, that is a discontinuity of a phase, will occur between the wave trains, between the two consecutive wave trains. So the caption is wave trains from a laser with coherence length equal to tau naught. So you see that each wave train has a coherence length equal to tau naught. A phase discontinuity can be observed between any two consecutive wave trains. The points A, B, C and D are the points of phase discontinuity. Due to this phase discontinuity between the consecutive wave trains, any point on one wave train will not have a definite phase relationship to any other point of the following wave train. Thus, the phase relationship between the wave trains is random. Consequently, if one of the wave trains is made to interfere with the other wave train, the interference will not be observable, because there is a random phase relationship of points on one wave train with the points on the other wave train. Now consider 2 points P1 and P2 on the same wave train, as we have shown over here. We have considered 2 points P1 and P2 on the same wave train. The 2 points will bear a definite phase relationship as long as they are located on the same wave train. The maximum temporal separation between the two wave trains should not exceed tau naught. That is, the points P1 and P2 can be at the extreme ends of the same wave train to have a definite phase relationship, beyond which the phase relationship becomes random. The corresponding length is denoted by L naught is equal to C times tau naught. So you see that L naught is actually the length of one wave train, which corresponds to C times tau naught, and is called the coherence length, or more precisely temporal coherence length. Now let's come to the property of the directionality. Directionality means that a beam of light has negligible change in its diameter as it propagates. Beam from a typical gas laser has high directionality, or equivalently small divergence. High directionality and small divergence are equivalent words. Directionality is linked with spatial coherence. High spatial coherence means high directionality. Even a beam with perfect spatial coherence always has non-zero divergence. Let me read again. Even a beam with perfect spatial coherence always has non-zero divergence due to diffraction of the beam at the aperture of the laser output coupler. A perfect spatial coherence has been assumed for the plane waves traveling within the laser. So you see, we are talking about within the laser. Within the laser cavity, a perfect spatial coherence has been assumed for the plane waves traveling within the laser capillary tube, as shown in figure 18.2, and incident on the semi-transparent aperture of diameter d of the output coupler. This figure. So you see that on the left we have shown a laser capillary tube, and the plane waves travel within the laser capillary tube. Some plane waves, when fall on the output coupler, they will leak through the coupler and form the output beam. On the right hand side of the output coupler is the actual beam coming out from the laser source. And you see that this capital D is actually the diameter of the semi-transparent aperture. Semi-transparent means that this part of the beam will be reflected back from within the laser tube, and part of the beam will be transmitted through this coupler. So that is why we have called it a semi-transparent aperture. And you know that we have shown the divergence of the beam with an angle theta d, and we have the observation plate at some distance, and point P is also shown on the observation plane. So capital P is the point on the observation plane. So let me read the caption. Diffraction of plane waves at semi-transparent aperture of the laser output coupler. So you see that here at the coupler, due to diffraction, divergence will occur. That is, the waves will deviate from their rectilinear path, and that is why we have shown the angle theta d. The outgoing beam will be diffracted at the aperture and will diverge by an angle theta d called the angle of divergence of the laser beam. From the diffraction theory, for diffraction limited beams, theta d is equal to epsilon naught times lambda over capital D. The constant epsilon depends on the geometry of the aperture. For a circular aperture, it takes the value of equal to 1.22. Referring figure 18.2, the field at point P, let me say again, now we are talking about the field at point P. The field at point P is due to the superposition of the fields contributed by the fictitious point sources located within the semi-transparent aperture. If the field incident on the aperture has partial spatial coherence, then the corresponding angle of divergence theta bears the relationship. That is, theta will be greater than the theta d value. And you know that we have defined theta d for a diffraction limited beam. And now we have defined this theta is actually defined for the partial spatial coherence beam, for the beam having partial spatial coherence, for which theta d is greater than theta d. Fictitious point sources lying within the limiting aperture of the area capital S with a subscript C. C stands for coherence. Fictitious point sources lying within the limiting aperture of area SC then coherently contribute at P, giving the divergence angle. So in that case, the diverging angle theta the divergence angle theta will be equal to epsilon times lambda over square root of SC. So you see that here we have considered partial spatial coherence of the beam with a divergence theta d, and the area of coherence is SC, and then the divergence angle for such a beam is defined as given by 18.4, that is theta is equal to epsilon times into lambda divided by the square root of SC. Even a weak laser source has a considerable high brightness, and this makes lasers a distinct source. Brightness, denoted by capital B, is defined by dP divided by ds into d omega is equal to B times into cos of phi. ds is the area of the source, generating power dP into the solid angle d omega in a direction which makes an angle phi with the normal to the area ds. So this is the general definition for brightness of any source. To use the equation 18.5 for a laser beam, we consider the schematic shown in figure 18.3, in which a laser beam is emerging out from the output resonator aperture. That is this. So the caption is diffracted divergent laser beam from resonator output aperture. So let me show the components of this diagram. You see that on the left hand side we have the laser capillary tube, and the plane waves are oscillating within this capillary tube. So the beam will diverge out. We have shown laser output aperture having capital diameter equal to capital D, having diameter equal to capital D, and the area of this aperture is pi into the square of D by 2. This is the area of this laser output coupler or the laser output aperture. and the beam is diverging out from the aperture, making a divergence angle equal to theta. And then we have also shown a laser spot at some distance away from the output coupler. So you see that we have extended the divergence angle inside the laser tube because we have gone backward from the laser output aperture backward towards the laser capillary tube, and we have extended these arrows backward which meet at some point at probably at the beam waist of the laser beam, and we have shown angle theta over there. Also we have shown angle theta at two places, and the angle theta is the same. And then we have shown the solid angle, which is d omega is equal to pi into theta square. So the essential components we have shown for this figure. Now plane wave fronts plane wave fronts inside the resonator diverge out at the output coupler or at the output aperture due to diffraction with an angle of divergence equal to theta. To use equation 18.5 for the schematic shown in figure 18.3, the following changes are introduced. So we are now introducing some changes in equation number 18.5 so that we can adopt this formula for the schematic of the laser beam shown in this diagram. For that one, we are transforming, that is dP will be replaced by capital P, ds will be replaced by pi into square of d by 2, d omega will be replaced by pi into theta square, and cos of phi will be equal to 1 because phi is almost 0 or nearly 0. The laser brightness formula thus makes the following form. So making these transformations in the previous formula, that is in 18.5, we obtain the brightness formula for the laser beam, and for the especially the scheme that we have shown over here, the brightness of the laser is given by capital B is equal to 4 times P divided by the square of parenthesis containing pi into capital D into theta. For a diffraction limited beam, we have theta replaced by theta D, and you know that the theta D is equal to epsilon times lambda over capital D, or equivalently we can say multiplying throughout the equation by capital D, we have theta times capital D will be replaced by theta D times capital D, or will be replaced by epsilon lambda. So making these changes in equation number 18.6, we obtain Bm. Bm is actually the maximum brightness. So Bm will be equal to the square of the term 2 divided by epsilon pi into lambda and then multiplied by capital P. So this gives the maximum brightness Bm of a laser beam with optical power P and operating at a wavelength lambda. This is the end of slide number 18.